Okay, so I'd like to go over one of these problems from the portable TA. This would be problem, question 6.6. It's from chapter 6, which is about forces. And we just started forces, so I thought this would be a good one. It also talks a little bit about kinematics, so this is a really good way to start thinking about how we tie forces and kinematics together. So I'll give you a second to read the question. You might want to pause and sit and sort of look through the question yourself. I highly recommend doing this before you actually listen to the video and solve the question. I would take this time to just try to do the problem on your own, at least try to set it up before you look at the answer, okay? Because the best way to go over these problems is to attempt them, and then you can go through the answer, and then when you think you understand what we're doing in the answer, it's probably best to do them again, maybe like 10 minutes later or an hour later, just to see if you really did understand it. Because if you did understand it, you should be able to recreate it. If you didn't understand it, then you might need to go back and look up stuff a little bit more. So I'm going to give you a chance to pause, look this over, and then I'll sort of go over the highlights of the problem and we'll go through the solution. Okay? So pause here. Okay, so we have this small railroad car, okay, so we're saying small railroad car. Let's start with railroad car. Here's the railroad car in the picture, okay. It sits on this track, so let's say here's our track, east to west track. So east to west track, that's this thing. And we want the eastward direction to be the positive x direction. So that means they're giving us a coordinate system, so we don't have to think too hard about what the coordinate system is. The car has a mass, so let's write down what we know over here. We have a mass of 7,500 kilograms. The horse pulls on a rope, so here's our horse. I guess I'll make the horse orange. The horse pulls on a rope attached to the car. The rope makes an angle of 20 degrees with the track, which is also an angle of 20 degrees with our x direction. The horse pulls with a force, P, equal to 6,500 newtons. That's the pulling force, but you could also consider it a tension force, depending on how you want to think about it. And then there's friction in the wheels, air resistance, etc., acts as a resistive force, so like friction and drag and all that stuff, that keeps the car from moving forward. Now, friction and drag and all that stuff means that we know this force has to point in the opposite direction of motion. Because as you look over here, we'll call this F sub r, and F sub r, it turns out, is what we're trying to find. It gives us a little bit more information, and this should strike you as kinematics information. So this isn't forces, right? This part is forces. This part is kinematics. So as the horse pulls, we know the car's acceleration is constant. That's a pretty key thing. Acceleration is constant. That should also tell you kinematics. So it gives us some kinematics information, and let's write that down. Let's write it down maybe in blue. So the kinematics information says that we know V initial is 0. We know V1, which is V final, is 0.60 meters per second, and we know our time T1, oops, not TI, is going to be equal to 5.0 seconds. So you can assume from that we're going to need to find acceleration because we knew that was constant acceleration. So that's the information we know, but let's start drawing a nice force diagram, because the first part of this problem, as you can see up here, that's going to be forces. Okay, so this whole section, this is a force problem, and we're looking for a force at the end. Okay, so here's our force problem. And then we have a kinematics problem we're going to need to solve to get to our force problem. So with all force problems, we want to start by drawing a picture. Now here I copy and pasted the picture, but you could easily redraw this. So what forces are acting on this railroad car? Well, we know there's a force in this direction. This is the F resistive, because that's the one we're trying to find. And the next most obvious force is just this force, which is a tension force, but they've labeled P. Okay. We also know the angle right here is 20 degrees, and we're given the coordinate system X and Y. Now I'd like to point out that there's a few forces here that we're not really going to need to worry about, but that I know exist, so I'm going to point out that they exist. So we can also notice in the z direction, right, if we want to add up all the forces in the z direction, we probably have weight going down and normal force pointing up. So that would be normal force minus weight, but of course since we don't have any motion in the z direction, this is equal to 0. In addition, once you break down, so we now have our coordinate system and our forces in the x direction, but look, this vector right here is in both the x and the y direction. So we have to break it into components, and that component is going to look like this, p cosine 20 degrees, and then also like this, p sine 20 degrees. Now we know that we only have acceleration in this direction. So what that means is we only have motion in the x direction, which means in the y direction, all of our forces, once again, should add up to 0. So the forces in the y direction, well, that's this, p sine 20 degrees, but also there should be another force that points, 20 degrees. There should be another force that points down that we're not really recognizing. And where does that force come from? Well, this is force from the track, okay? Because the railroad car can't go in this direction, so there's force from the track that keeps it trapped on the track. And so it turns out this force and this force are also going to go away. Whoops, let's do it in black. So this minus F track, that should also equal to 0. So even though we do have forces in the y and the z direction, we're not really going to need them to solve the problem. And so these equations, although they matter, they're not going to give us any information that we need for this problem. What we care about are the forces in the x direction. And the reason we care about that is when we add these up, p cosine 20 degrees minus f sub r, these are going to be equal to the mass of the railroad car times the acceleration in the x direction. Now you notice these are 0, but really this is equal to mass times acceleration in the z direction, which is 0. And this is equal to mass times acceleration in the y direction, that's equal to 0. This is just Newton's second law, which says F is equal to ma, but of course it's a vector, and it's the net force. You have to add up all the forces to get net force. So we're just doing Newton's second law over and over and over, and it turns out we don't actually need these things, so we're just going to get rid of them. Hang on, we'll erase them. But it's important to always know that those forces exist, and then we're going to just deal with stuff that's happening in the x direction, because look, all of these forces, this force, these are in the x direction. This acceleration, this is in the x direction. So we're only worried about stuff that's happening in the x direction. Now we can solve this for our resistive force. So F sub r, that's going to be equal to p cosine 20 degrees minus max. Okay? Now we want to figure out what we know and what we don't know. So we know P, look, P's up here. We know this 20 degrees, that was given to us. We know M's up here. What we don't really know yet is A, and that's the only thing we really need to get our final answer, which is this resistive force. But we are given enough information to get A, and that information was given to us in the second part of the problem, which we called kinematics, okay? So this is the kinematics section of the problem, okay? And we already wrote down the information we need to do that part of the problem over here. And all we really need to do is solve for acceleration. And more specifically, this is acceleration in the x direction. And it turns out our very first, most straightforward kinematics equation, A is equal to delta V over delta T, will work. And the reason this works, this is constant. And we know it's constant because it says acceleration is constant. So it's pretty easy to assume that. This equation is sometimes also written V final is equal to V initial plus a delta t. And you can see if you do some algebra, these things are pretty interchangeable. But since we just need the acceleration, we can write it this way. I also want to point out that normally acceleration, the definition of acceleration is dv dt, where this is a vector. In this case, we don't have to write it as a vector because remember, we know this is in the x direction. But the reason we can write this as this difference instead of a derivative is because this acceleration is constant, and that is the central assumption in our primary kinematics equations, those three equations with the v finals and v initials and all that jazz. So when we solve for acceleration, let me clean this up a little bit. When we solve for acceleration, what we find is we have v final, which is v1, minus v initial over t1, because t initial should also be 0, so we could write it like that. That comes out to be 0.60 meters per second minus 0 divided by 5 seconds minus 0. When you put all this together, you get 0.12 meters per second squared. So that is our acceleration in the x direction, which is what we were looking for to finish off this problem. So now we have all of the numbers we need because this plugs back in there. So P, that's going to be 6,500 newtons cosine of 20 degrees minus M, which is 7,500 kilograms times 0.12 meters per second squared. Sorry, we ran out of space there. And when you plug all this stuff in, you end up getting a value. That value looks something like 5,200 newtons. You know, the other thing to keep in mind is make sure your calculator is in degrees, not radians, just to make sure you get the right answer. But what you'll see here is we have both a force problem where we want to draw out our forces, pick our coordinate system, break things up into x and y, and then sum up. And we also had a kinematics problem, which goes back to our first three chapters. That's it. Tell me what you think.